Today's speaker is Professor Maria Rodriguez. She has just recently joined us here in the physics department at USU, but her career has taken her all over, well, her life really, has taken her all over the world. She started her life in England, in the UK, did some of her growing up in Argentina, did her college and graduate work in physics, specializing in black hole physics, in Spain. Then she had research fellowships, which took her to Germany, the Max Planck Institute, then to Harvard, which is where we were lucky enough to grab a hold of her and convince her to come to USU. We're very lucky to have an expert in black hole physics here to tell us all about it. So I won't use up any more of her time. I'll just hand you over to her. So, Maria.
Thank you. Thank you, Charlie, for this introduction, and good evening, everyone. First of all, I want to thank the organizers of the Science Unwrapped for having me tonight. And also I wanted to thank the College of Science for supporting this event tonight. So we will be talking tonight, or I will tell you some things about black holes. And the idea is because these objects do commit some awful crimes here in the universe. So we will have, and we will see some crime scenes, and we are going to try to see whether we understand what crime they're committing. Okay? And although it sounds scary, they're kind of scary, but not so much. We are going to see these crime scenes and all these properties about black holes. So do everyone know what black holes is here in the audience? No? Yes? Yes? Okay, very good. Perfect. So I will be talking about black holes. And by this, I don't mean these black holes in the backyard of your homes. Okay, so black holes, I will not be talking about the ones we found here on Earth. I will be talking about these black holes out in the sky. And these black holes, which are depicted here as an artistic representation, is this sphere that you can see here against the background of some stars. Okay, so we are going to be talking about these stellar objects that have extraordinary effects, and they actually change the way we see the sky, and they exist out there. Okay? So what are exactly black holes? So do you know who this person is? Albert Einstein. Okay, so today we are going to be talking about black holes. But without Einstein's ideas of black holes, we would not be probably talking about black holes. So Einstein brought these ideas from a theory called general relativity, and we need that theory and certain aspects of those to find mathematically and describe these objects. But as we will see, they are also seen experimentally, but we understand them and can describe them in a more formal physical or mathematical way by using Einstein's ideas. So within the context of the ideas of Einstein's, you can think about black holes as some cosmic, or the eyes of a cosmic hurricane. And this is an artistic work where the black hole is kind of swallowing everything that gets close to it. Okay? So anything that happens to travel past or very close to the black hole will end up probably, or most likely, in the black hole. And it will have a very hard time to prevent that from happening. So what is the difference then between a star and a black hole? Does anyone know what that is? Yes? Okay, so stars don't suck in planets. That's one aspect. That's right. That's a very good way of distinguishing them. Yes? Mm-hmm. Perfect. So we've seen lots of things about black holes. Just a minute. So one aspect is that black holes are black, and we're going to see why that is, while the stars are usually bright, okay, and they emit light. Yes. Stars are different colors. What else? The black holes what? Sorry? They glow, exactly. So those are very many different things we know about black holes, and the Schwarzschild radius, we'll talk about that in some other way. But the main difference, now we will stress what the main difference is. So let's think that we are going on a spacecraft from the Earth to the star. And probably because the stars are also very, very hot, we'll burn if we try to land on them. But let's think we are okay. But in this mission, the best thing about stars is that when we are homesick, we turn the engines and we come back to Earth. Okay? But what happens with the black holes? If I want to fly and go and see what a black hole is, I will probably be able to approach it and very, very close to it. But when I want to turn around and come back from it, I will not be able to do that. Okay? So that's the biggest difference between a star and a black hole. Yes, you have your hand on up. Yes. Because of gravity? Yes, we are going to talk about the gravity, of course. That's going to be important in black holes. Okay, very good. So that's the main difference. And the surface or the place in the universe where we are not going to be able to turn around and return, it's called the event horizon. And we don't really care about the word for that, but it's the place as if you are crossing into a room and closing the door, and now after you're in that room, you will not be able to open it and come back out of that room. That's the event horizon, or this surface that defines how large these black holes are, and they're surfaces of no return, okay? This is the main difference between the black holes and the star. So somebody mentioned actually just a minute ago, so what causes these black holes to gobble up everything inside? And the answer to this is gravity, okay? And it was kind of sort of well depicted in the film. Maybe you saw it, maybe not. And there's no black holes in the movie, but it is a movie about gravity. And gravity, for those of you who don't have a way to explain that, is one of the forces, okay, in physics. That's the way we distinguish things. We just call them forces. It's one of the forces that keeps the planets in our solar system going around the sun, okay? And it is the force that keeps us here on Earth from falling and leaving into outer space, okay? So gravity is, if you want to measure it, and you go on a scale, the weight that you have. And the more mass you have, the stronger or the heavier you are. That means that the Earth is pulling you harder. And if the Earth is larger, it will also make you or being attracted more towards the Earth. So that's gravity. And gravity will have a say in what these black holes are. So one aspect that we can think about is, why are black holes actually black? Well, if we do the following experiment now, we are sitting on the Earth and we just speed up some spacecraft, and the spacecraft starts flying out from the Earth. The Earth creates some gravity, and so the spacecraft, if it's not flying very fast, will turn around and come back to the Earth, sort of as whenever you're throwing something and it comes back. But if you speed the spacecraft very, very fast, it will be able to avoid the force of gravity, and it will leave the Earth behind. So, but what happens with the light? Light travels also very, very fast. So it can actually escape the gravity of the Earth. And it goes straight in this way. So if you have a lighthouse, for example, you could see the light beams actually flying across the universe. But if you start shrinking the Earth and you're pulling it into a point and making that denser and denser towards one singular point, then the light will start bending with it, okay? And it will not be able to escape so much. Up to the point when you continue doing that and you put the Earth into just a single point, that the escape velocity or the light will not be able to escape, and it will turn around into the same point where it started. And this is why, actually, black holes are black. They're so dense, they have such a strong, strong gravity that whatever wants to fly out, and even light, will not able to escape. It will turn around and go back to the same point. And this is what makes black holes black. So black holes, if you want a more formal definition, is an object that is so compact that anything, not even light, can escape the gravitational field or pull or force that exerts. So why are black holes so interesting? And in particular, they're so interesting in science fiction movies. It is because they have very interesting and very strange properties. And some of the movies that feature them are perhaps the worst movie ever on black holes. Not probably everyone saw it, and if you see it now, it was a film in the 80s. It has the worst effects. It is the most inaccurate, scientifically incorrect movie I've ever watched about black holes. So this is one. But then time went by, and we realized that actually we want to know more about movies and science facts, not science fiction. And so recently there was this movie called Interstellar that is very, very accurate. And it not only has black holes in them, but there was a lot of information of the scientific community given to the film and simulations that are pretty accurate of what happens out in space and what happens when you approach or see black holes. And one of the persons involved in this adventure of trying to work and collaborate with Hollywood was Kip Thorne. And probably all of you know he is originally from Logan, and so he participated in this. And we will talk just a bit more about Interstellar's black hole that's called Gargantua later in the talk tonight. So black holes appear also on cartoons, and not everyone may know them because they don't show up in the Octonauts. But the cartoons are, for example, in Futurama. This is very, very inaccurate. You will not be able to have a black hole in your wall. And the other cartoon, well, there are many, but this is The Simpsons also had black holes at some point, and they were swallowing all the family and the town and the mountains and everything around them. So you can find, if you're interested in finding in which films you can see black holes and how accurate they are with respect to the physics, in many websites. This is the one I found was very complete, so you can enjoy yourselves while it's raining and find some good or very bad movies about black holes. Okay. So in the introduction, Charlie mentioned some of the things in my trajectory, but I wanted to tell you, my motivation, not Hollywood's motivation of why I want to study black holes. So when I was little, I started liking math, so I played the Math Olympics. And there were 2 books and TV shows that caught my attention at that time. One was The Elegant Universe. I don't know if you read it. It's a very boring book, but the TV show was pretty good. And then it's kind of dark there, but it's The Brief History About Time of Hawking. He was talking about string theory and black holes. I didn't know anything about it. And so I was in a females-only school, as you see in the picture here below. And I decided to go to the physics department in Argentina and study physics. So I ended up doing my PhD in Barcelona and wrote a thesis about black holes because I was so intrigued by these objects. And then I went on and studied and did a postdoc at the Max Planck in Berlin, followed by some time at Harvard before joining here USU with my family. So nowadays, the university pays me for 2 things. One is teaching, but the other part is doing research and understanding, in particular, what these black holes are and the properties that they have. So still, so many years pass, and my questions about black holes are still unsolved, but this is what I do here at the university. So, well, this is kind of like a long introduction, but let's look at the crime scenes these black holes are committing in the universe, okay? So, the first crime scene I want to show you tonight is this one, which is a depiction or an artist's work of what the Milky Way looks like, okay? And in this Milky Way, which is our Milky Way, the solar system, is standing somewhere here around one of these arms. And what you see is a crosscut of the Milky Way, and they're arms of dust and matter that is swirling around a certain point here, okay? And so all of this is moving towards a center. And we didn't really understand why this was happening. And so one of the ideas is now to try to think how far away, or understand how far away we are from black holes, and also to see if the Earth is very close to one, because then we should start getting scared of them. So the Milky Way looks like this. And I did a very, not very accurate experiment, because I'm a theoretical physics, I'm allowed to do that. So what I have here is I want to show you, so if this is the Milky Way, and I want to put a black hole in this Milky Way, where would you put it? Well, if you put it somewhere here in the corners, and you start turning around things, you will see that the ripples actually are close to the edge. And this doesn't really look like the Milky Way, right? So if I want to do this, if you don't see that in the back, this looks like that. This was last night's picture, so sorry about that. So the other option would be to try to put the black hole in the center and start seeing what gravity is doing. So if I turn my cloth around, you'll see the ripples are actually more towards the center. And this looks much more like the Milky Way picture that we have down there. So in this world, if we have the 2 black holes, which are these dots here, it would make sense to actually not have a Milky Way with a very, very large black hole in one of the sides, but in the middle. And actually, this is what happens with the Milky Way. And in our galaxy, there is a supermassive black hole in the center of it. And we checked that, and I will show you how we did that, and found that black hole in the center. And this would probably now that we know that there's a supermassive black hole in the center of our galaxy, makes sense when we look at the picture of the Milky Way. Because before, where was all this matter, the stars and everything falling into? Well, they were falling into a supermassive black hole. So this is the map, if you want, of the Milky Way. In the center here, in red, is the supermassive black hole that I've been talking about. It is 4.5 million times the mass of the sun. We can't even think what that is. It doesn't matter. It's called Sagittarius A star, and that is our supermassive black hole. It is the closest supermassive black hole to the Earth, and so it will be easier to study that one instead some other ones that are in other galaxies. The other smaller dots here are actually also black holes, but they are tiny. They're in comparison with the one in the center of the Milky Way, they're called stellar mass black holes, and they're going to be smaller than those. So where are we in this map? Where is the solar system? Well, the yellow spot there is actually the solar system. And so we are not so close to the center of the Milky Way, but we are close to the smaller black holes. And these are the distances and dimensions of how far away we are from the center of the Milky Way. Okay? So how do we know for sure there's a black hole or a supermassive black hole in the center of the galaxy? Well, what happened was around the 90s, in the 95, some telescopes started looking at the center of the Milky Way, and two groups, mostly in California and a competing group in Germany, started looking at that center, which is depicted here with a small white star. And because no light was coming from it, we couldn't measure directly whether that was a black hole or not. So what do you do if you're a physicist interested in that? You will look at all the other things, which are this purple and green dots there in that video that I'm going to show you, and look what or how they're moving in space. So I want you to first look at two things. This is a center where it could be potentially where this black hole could be. And the other thing is this here. This is the number. It is July of 1995. And we started looking and taking data, looking at what all these other objects were doing. And we started collecting data and seeing and tracing the orbits of all of them. So look at the corner, 2006, 7, 8. And in 2010, the first complete orbit of one of the objects was measured. And that is all the information we needed. So from 95 to 2010, it took quite a long time. So when we know the orbit, we can tell which big object is in the middle. And because of that, the only way to make those orbits and those objects go so far, and in particular in those orbits, the only explanation was to put a black hole or a supermassive black hole in the center of the galaxy. And so this was a proof that actually in the center of our galaxy, we do have this supermassive black hole. So, moreover, we think nowadays that not only our galaxy has one supermassive black hole, but every galaxy should have one. And this will change the environment of the galaxy and how they look. So how do black holes form? We will just do an experiment tonight for it, and this is our big can here boiling. So James Colburn agreed to help me doing this experiment tonight and will explain to us what we are going to do next.
All right, so we've got a barrel here that's had 2 liters of water in it. So you know what 2 liters is. That's what you buy a bottle of soda, right? So it's got 2 liters of water that's been boiling happily there for about 15 minutes. And so in that time, we should have pushed most all of the air out of the barrel and replaced it with steam. And so at this point, I'm going to get up here where I can turn the valve. And if you'll turn the burner off, go ahead. So I want to trap that steam inside of there. Now I've got a barrel full of steam. And what happens to steam when it cools off? It turns back into water, right? So most of the time, a barrel is balanced. It has air on the inside, air on the outside. It has something on the inside with equal pressures. Well, in this case, we're going to unbalance that pressure. We've got steam inside that's cooling now, and we're going to help it cool by sitting it in some ice here, adding some ice on top, spraying it with cold water, and we're going to see if we can get it to condense, and then there's going to be low pressure inside, and there'll be the atmospheric pressure outside. Should we try this?
Yes.
It was hot. I think it's going to go good. It's ready. You want to go on that side?
Yep.
Okay, so we're going to spray it with a little water. Sitting in ice, got ice on top of it.
So, thank you, James. So what happened? What just happened? There was an implosion, okay? So let's try to think whether we can use this concept to learn about black holes. So what happened was the pressure outside was very high in comparison to the pressure inside, and so it crashed the barrel. And something similar happens when we think, or this is what we think happens with the black holes. So we have a star, and the stars are burning its fuel. And at some point, the star burns all the fuel it has, and it cannot actually prevent the collapse, okay? And so this is what we think happens also with the stars. And so the death of the star will be the birth of a black hole. This is how we think they form. And this is a cartoon of what we think happens, which is pretty similar to what we have here, but the other pressure is just the gravity doing this effect of pulling everything into a point and forming black holes. So could we also make a black hole out of the Earth? And the idea is, and the answer to that is yes. So you would have to shrink all the mass of the Earth into one point exactly, to a point where you see a peanut, and you would form a peanut-sized black hole. So we can do black holes as we can do stars or implode cans for every object in that we can think of, but we have to put them or pull them together in a very small region, and that's called the Schwarzschild radius, or the very small size. So now, after doing this, I want in the last 10 or 15 minutes to talk about something different, which is, and I will skip this part because the experiment took a bit longer than I expected. We would try to see what we feel when we fall into a black hole. And everyone probably thinks that they saw the ultimate movie on how to fall into a black hole. But we will see that maybe there are some misconceptions of what happens when you fall into a black hole. And so that is the last crime that they do commit today that we're going to see. So are you afraid of black holes? Someone? Yes? Yes? Yes, you like them? You feel, yes, they're cool? Okay, good. So, well, you shouldn't be that afraid if you're thinking that something could happen to you when you're crossing that surface of no return, okay? Because it will depend very much on how big the black hole is. And so there are two ways of falling into a black hole. One of them is, and this is the most scary one, if you fall into the stellar-sized black holes, the ones that are smaller, although we think bigger beasts or bigger objects should be scarier. Well, that's not the case. Actually, smaller black holes can be more harmful than the larger ones. And I will show you why that is. Well, if you are around a black hole and you're falling with your feet towards the black hole and approaching it, you will see something like that. Okay? So your feet are going to get first into the black hole but stretched, and you will feel a pull that is very, very much bigger in your feet than in your head. And you will start to become like a spaghetti. That's what's going to happen. It's probably going to hurt. And you're going to be a very thin spaghetti, a one atom line before you pass through the event horizon. So we don't want, as being the Earth or some person, flying into a stellar mass black hole. And this effect, why is that? Well, when you're approaching the black hole, gravity is so different, just a minute, in your feet and in your head, that it's much larger, the force in your feet than in your head, and so the pull is greater and you become a spaghetti, okay? So if you get your Play-Doh and you start pulling from one side, you get stretched, well, that's what happens here. Yes? We don't know. I think it will hurt. But we are not going to fall right now into a black hole. So don't get scared, okay? It will take us very, very long time as the Earth to fall in any of those black holes. Did we have another question? No. Okay, so this effect in physics is called spaghettification. I said I liked studying black holes, and no one warned me of these funny names for things. So this is a theoretical process because we have never fallen into a black hole, okay, where an object gets stretched when it feels the gravity being close to a black hole. So this is option number one. And then we have Interstellar. So in Interstellar, let me remind you, this is a scene I took from them. So what do we see here? If you haven't watched the movie, this is a spoiler of it, so leave, please. So this is the black hole. Here, a very, very large mass, okay? And yes, she is somewhere here, okay, in this spacecraft. And Matthew McConaughey decided at some point to do a not very clever thing and fly into the black hole, okay? But in the movie, what happens? He flies into the black hole, and here's the big, big spoiler, so I'm not, okay, so I'd say it. So he actually survives falling into the black hole and lives a different life in some hidden or bigger, higher dimensions inside of the black hole. But what happened with the spaghettification? Someone is wrong. Is it me or Hollywood? What do you think? Hollywood? Well, actually, we are both right. I tell you why. This black hole is not a tiny black hole. Gargantua in this movie is a very, very large black hole, and it's a supermassive black hole. So it is one of those big objects we have in the center of the galaxies. And that makes a complete different problem. Because it doesn't matter how large the object is, but the distance to the center. And we are very far away from the center when you try to enter the supermassive black holes where these surfaces of a novel event are there, but we are closer to that singularity or special point when you're in the closest, in the smaller ones. And that is what makes the spaghettification start. So if we now think about Interstellar, but I will show you a true movie or a journey into a black hole. And this is not Hollywood, this is a numerical simulation. That is what we do in the physics department. We simulate things or solve things. And we are going to use the theory of general relativity. I did not do this movie. It was a group actually in Virginia who made that. And they rendered this, so they made a computation and they produced these nice videos by using general relativity, and that is what I'm going to show you. So this is what you, if you were going to fall into a black hole, would see, okay? Not a person, your mom at home and you're running away to the black hole. This is not what your mom is going to see. It is what you are going to see when you fall into the black hole. So two observations in here. You will see in this simulation around here some crosscut of the different surfaces you're going to go through, and in red, very big red, you will see when we are close to the event horizon and crossing the event horizon. Okay, that's going to be here. And this black hole, to make it realistic, does have something called the accretion disk. So when you fall into the black hole, there's a disk, like the rings you see in some of the planets, and that is an accretion disk. And everything starts moving in that kind of donut-shaped disk into the black hole before it enters the other regions of the black hole. So you will see that information here in the bottom of where we are when we fall into the black hole. And so we will now play this simulation here. Okay, we start falling into the black hole, and this is what you see, some light. Okay, we're safe here, that's not a problem. There's some jets that are coming out. We are not going to be talking now about them, but you see light. And we're now in some place called the unstable and stable circular orbit zone. And we are now crossing the event horizon, the no return region. But nothing happens. And we're inside of the black hole, and we will start seeing light and more light and more light. That is what is actually going to happen if you fall into a black hole. So the spaghettification only occurs for the tiny black holes, but in Interstellar, and if we fall eventually in the black hole Sagittarius A in the center of a Milky Way, this is what you should see when you fall into the black hole. So we solved certain crimes tonight, so I'm kind of in the end of my talk. So we found out where black holes are in the Milky Way, and this is very important if you didn't know that. There are plenty of them in our Milky Way. There's only one that is very supermassive. We did a very cool experiment and showed how black holes are born. We haven't talked about the black hole jets, and we fell into the black holes. And there are two ads I wanted now to share with you. One is we started a USU Women in Physics group, and we're going to have a table downstairs. You're welcome to come and talk with everyone in the table. And they're going to be organizing a workshop for girls from 9th to 12th grade. So everyone is invited for that. And if you want more information, you can get that in the table downstairs. And also I belong to what's called the DG Camp group. It's a research group here at the physics department jointly with the math department. And we do have a table downstairs, so if you want to have more fun with black holes or have more questions about it, we will be downstairs um, 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 talking to you. And the last thing is, if you have any questions also in Spanish, I also speak Spanish or Espanol, so you're welcome to make them. So that's everything for tonight. Thank you. Yes, thank you. So questions? Yes. So how long will it take the Earth to fall into the black hole? Well, it will depend which black hole we are talking about, and there are other circumstances that we don't really know, but it will take millions and millions of years to do that. So we are on the safe side on that. Yes? Will it be warm or cold to fall into a black hole? Well, the black holes, in comparison with the stars, are very much warmer than the stars. Okay? So I think it will be a bit more hotter. Yes? So the question is there any other, or is there any dimension, extra dimension inside of the black holes? Well, that we don't know. We think there isn't extra dimensions in the black holes, but we can't say because no one has gotten into a black hole and came out. And currently the theories don't tell us exactly what happens inside of the black holes, okay? Just a minute. Sorry. Yes? What happens if you hit the middle of the black hole? That's a good question because the middle of the black hole is called a singularity. And a singularity in physics is not good because it does mean actually two things. It means we don't have any experimental data. And the worst part for me, because I'm a theoretical physicist, is that there's no theory to describe what goes on there. So everything breaks. But most likely it will be a very singular point, a point where you are going to see everything crashing down very fast. Yes?
Would we die if we fell into a black hole?
So would we die if we fall into a black hole? Well, the question is fine, but we have to distinguish between these two scenarios that I told you about, whether the black hole is smaller or larger. If you're feeling spaghettification, probably there's no way of being an atom-sized spaghetti into a black hole. But if you're falling into the center supermassive black hole, you will be fine crossing it. I don't know if you will die in the center or in between that, but those are the predictions for those. Yes? How small can a black hole be? We really don't know that because from general relativity, we think that anything that you can pull into a very small region and you make it very, very dense will collapse and become a black hole. So in principle, if two atoms occupy a very small region, probably you could generate such a small black hole. And there are some theories that say that there are some mini black holes out there. But so far, we haven't detected them. So sometimes when you don't see them doesn't mean that you don't exist, but there's no proof of the contrary. Yes? Like what? Portals, yes, they are sort of like that. But there's another concept that I did not talk today about, which is a wormhole. Okay, a wormhole connects two, or this is the theory, connects two different places on the space-time. So they are kind of portals, but it doesn't mean that you enter that and you go through some worm into some other parts of space. Okay? Yes? So you mean if gravity is very, very strong in black holes? Yes, that is right. Yes. More questions? Yes. So what is the function of the black holes in the creation of the universe? We really don't understand the whole role they have. But as you can see already in this way of looking at the Milky Way and understanding that actually it makes total sense that all this matter is falling into a black hole and not something else, it starts to give us clues that black holes did have a role in the cosmic evolution of the universe. So I'm not giving you an exact example of what the roles were, because we haven't fully understood what the roles of black holes are in cosmology. Yes. Can black holes die? Yes, they can do something, which is they can actually evaporate. So, and this is a process in quantum mechanics, and they could actually disappear, but we haven't also seen that. So, those are theories so far. Yes?
So if the whole Milky Way goes into the massive black hole in the center, does that mean that one day the Earth would be inside a black hole?
Yes, that's so. Yes. If nothing else happens, because it could be that we end up colliding with some other galaxy. Okay? But if nothing else happens, in the end, everything would be swallowed by the supermassive black hole in the center. Yes?
The middle black hole of the Milky Way, what would happen if it evaporates?
Oh, what happens if it evaporates? That's a great question. Charlie. Okay, well, it's a very good question, and so far I think we don't have answers to that. Yes. Yes.
Will you please tell the kids how long before we hit the black hole, because they won't sleep tonight?
This is millions of years. It's never going to happen at this point, okay? So you go home and sleep. It's going to be fine. No worries. We're here taking care and watching the black holes doing their stuff in the universe. Yes? The smaller black holes would have smaller gravity because they can only hold, or they hold less matter, so they are less powerful in that sense. Yes, up there. If you what? Phase? Oh, it doesn't matter. You're probably my hair, okay, will fall first into the black hole, and then my head, and then my feet. But it will be the same thing. I will feel the same spaghettification if we fall in the small ones. If we go in the big ones, that would be no problem. We can go anyway, sideways or whatever you want to. Yeah. Okay. Yes.
Can black holes grow?
They can grow. Okay, the more matter they have, they probably start growing and growing. Yes. Yes, up there. Oh yes, they were there. Black holes have been here in the universe for a long time. Yes. They were here at the same times as the dinosaurs. Yes. Sorry? Ever grow? Erode. Well, I'm not sure about that. Yes. Yeah. What is the biggest black hole? Well, one of the biggest black holes we know of is called Zenus 87, I think. But that doesn't mean that it's the largest black hole in the universe, or even, the closest to us, because we haven't explored so many black holes. We haven't had the technology to do that. And now there's the second step is to convince the federal agencies to give us the money to figure that out. Yes. From here, we can leave if you want. Yes, no problem. But you're welcome to stay as well. Yes. So why did I decide to study black holes? Well, black holes were very intriguing, and for me, math was kind of easy, but I didn't want it to become a mathematician. It was too abstract for me. So I thought I should apply this to something else, and I started studying physics. And although I never dreamed as a girl to become a theoretical physicist working on black holes, I ended up doing that. And it currently pays my rent, so I'm kind of happy doing that. Yes.
Do we know anything about what happens to matter inside? Does it break down to, what happens to matter?
It is a risky thing to say what happens because I described everything with simply gravity on it. And there's also quantum mechanics and other theories. And we really, really don't know what happens after you cross the event horizon or the no-return surface. Yes? Mm-hmm.
Can you explain whatever theories there are that led them to say that all that light is in there?
So for that, we would have to go and look in more details into general relativity and how the simulation is done. But this is pretty much what we think is going to happen. Yes. Yeah.
Does light have mass, or how does light get sucked into a black hole if it doesn't have mass?
Well, the light, if you want to think about it, is also an object, or it has some energy, and if you want to associate mass to it or not, then that will make it feel. So light feels the gravity pull and will fall into the black hole. Okay? Light, yes, yeah. So it falls into the black hole and feels gravity. So we say it interacts with it, right? What else? Yes.
So we're talking of a black hole that sucks everything in sounds very threatening, right?
Yes.
But are there also positive theories about something positive? Maybe it's kind of along with that function question, I think. A function to what it is. Or are there theories about what the function in a positive way could be?
Well, black holes not only suck things up, but they made the way we circulate in the Milky Way in such a way that it is smooth and we are not flying out somewhere in the sky. So they have the same effect. Maybe we don't understand as much as what is the relevance of them as the sun that gives us light and warmth and life on Earth, but it does at a big scale give us an idea that we are not flying out in the universe, and for some reason, and most likely they do have a big role in how we evolved to become a solar system and life on Earth. Yes, up there. Okay, very good. So black holes, I did not talk about that, but black holes are neutral. They don't have a charge on their own. But there can be electromagnetic fields around them. So if you're a charged particle falling into the black hole, you will feel some electromagnetic field or some magnetic field. And so what happens is the black hole starts rotating this field, and in the end, instead of falling into a black hole, you could be ejected out as the dragons do, in two jets coming out from the black holes. So although black holes do not have a charge, there can be close to the black holes electromagnetic fields that would generate some very other different properties that I haven't talked about that help you not falling into the black hole but fly away from it.
This would be a good place to stop. If you want to ask Maria more questions, please feel free, and let's thank her again. Please.
Thank you.